Hello everyone. In today's lecture, we will talk about the theory involved in the heat transfer in turbulent flow experiment. The experimental procedure is almost same as that of laminar flow, and setups are also similar. As we can see, this one is the laminar flow setup, and this one is the turbulent flow setup. Both are similar. Only difference is that rotometer in the turbulent flow setup, which is installed for measuring the cold fluid flow rate, it can measure the higher flow rates compared to the laminar setup. Otherwise, both are similar. This is the cartoon of the setup. Cold fluid comes from the tap, enters the rotometer, exits from the other end. Thereafter, it enters the outer pipe of the heat exchanger, and then it exits from the other end. Hot fluid is pumped from the storage tank, then it enters the inner pipe of the heat exchanger, exits from the other end, then it goes to the cylinder, exits from the other end, then it again enters the storage tank. The flow rate of this hot fluid, which is water, is controlled using this valve. Before doing any calculation, we must know what we have to find from the experiment, what we have to estimate. In this experiment, we have to find the overall heat transfer coefficient with the help of logarithmic mean temperature difference. After that, we have to find the individual heat transfer coefficients with the help of overall heat transfer coefficient. And in the last, we have to verify the empirical equation for the turbulent flow. Here in this experiment, cold fluid flow is kept constant. We have used 300 lph. This is kept constant throughout the experiment. For the hot fluid, different flow rates are used, and the flow rate is measured using this cylinder. Many manufacturer companies install a rotometer rather than this cylinder. The reason is that the rotometer can easily measure the higher flow rates, which is the demand of this experiment. But cylinder can also be used. If in every setup rotometer is installed, then you need to find the minimum flow rate so that the flow of the hot fluid is in turbulent region. Here in our case, we need to find the minimum time for filling this cylinder from the bottom to the mark place so that the flow of the hot fluid is in turbulent region. So that minimum time we need to find. Procedure is same as we did for the laminar flow. In the case of laminar flow, we found the maximum time. Here we will find the minimum time. So for that we will use the Reynolds number concept. Reynolds number is equal to di u rho by mu. Di is the inner diameter of inner pipe. U is the velocity of the fluid inside this inner pipe. Rho is the density of the fluid, and mu is the viscosity of the hot fluid. This u we need to find, that can be found from here, from the cylinder. The particular height for which we are filling the fluid is known, that is h, from bottom to the mark place. Therefore, we can find the velocity uc is equal to h by t. And after that, we can find the volumetric flow rate of the hot fluid in the cylinder, qc, ac into uc. AC is the cross-sectional area of the cylinder. If diameter of the cylinder is d, then we can do pi d square by 4 into uc. This is the volumetric flow rate of the hot fluid in the cylinder. There is not much significant difference in the density of the fluid. Therefore, we can equate the volumetric flow rate inside this cylinder and inside this inner pipe. Say the volumetric flow rate in the inner pipe is QH, and QH we can write AH into U is equal to this one, pi d square by 4 into UC. UC is nothing but h by t. So we can write here pi d square h by 4 into t. And from here u is equal to pi d square h 4 into t into AH. AH is nothing but the cross-sectional area of the inner pipe in the direction of flow. If this diameter is di, inner diameter of inner pipe is di, then we can write pi d square h by 4t into pi di square by 4, and then we will have. So from here we can find the velocity of the fluid inside the inner pipe of the heat exchanger. Once we find, we can put at this place, inner diameter of the inner pipe is known, density and viscosity both are known. These two should be considered at the mean temperature of the hot fluid. For example, if inlet temperature is 70 and outlet temperature is 50 for the hot fluid, then average temperature will be 60, and we should consider these two values at 60 degree. Now I put the velocity at this place. D square h rho by di mu into t, or we can write t equal to d square h rho by di mu re. For the turbulent flow, Reynolds number should be more than around 4000. But we have to verify the Dittus-Boelter equation, which is well applicable for the fully turbulent flow. So for that, flow should be very high, and the Reynolds number should be more than 10,000. Re should be around 10,000, 10 to the power 4. When Re is greater than 10 to the power 4, and here we have the inverse, therefore T should be less than d square h rho by di mu into 10 to the power 4. Here in our setup, we find t which is less than 3 seconds. So that means we have to fill this cylinder up to this marked place from the bottom within 3 seconds. In that case, Reynolds number will be more than 10,000. And flow will be fully turbulent. Using this control valve, we can adjust the filling rate so that time should not be more than 3 seconds, or whatever in your case after calculation. Similarly, you can do the calculation for the volumetric flow rate, minimum volumetric flow rate if you have rotameter. In that case, at the place of velocity, you can put volumetric flow rate by area. Now we will do the calculation for the overall heat transfer coefficient that we have already seen in the laminar flow experiment. I write rate of heat transfer, verified rate of heat transfer. Heat is transferring from hot fluid to cold fluid, this way or this way, from inner pipe to outer pipe. Say inlet temperature of hot fluid is TH1, outlet TH2, for the cold fluid TC1, TC2. So delta TLM, that is the log mean temperature difference, logarithmic mean temperature difference, temperature difference at the inlet, temperature difference at the inlet, temperature difference at the outlet, divided by ln this one TH1 minus TC1 divided by this one TH2 minus TC2. All values we know for a particular flow rate. AI is nothing but pi di into L. Di is the inner diameter of inner pipe, L is the length of the pipe. In this case, we have to take the surface area of the pipe, not cross-sectional area. Of course, this is also cross-sectional area, but in the direction of heat flow, not direction of fluid flow. And now next we need to find the Q dot, that is the rate of heat transfer. So this can be found from the heat lost by the hot fluid in a particular time. So Q dot is equal to mH Cph Th1 minus Th2. mH dot is the mass flow rate, which can be found from the density into volumetric flow rate QH. Here volumetric flow rate inside this pipe is same as that of volumetric flow rate in the cylinder, that is QC. I write directly QC. Cph Th1 minus Th2. And using these two equations we can find the overall heat transfer coefficient. For different flow rates we can find the different overall heat transfer coefficients. Now next we will do the calculation for individual heat transfer coefficients. We know that the inverse of overall heat transfer coefficient, that we have already seen in the last video. For the case of laminar flow, 1 by Ui is equal to 1 by Hi plus xw divided by k Alm into Ai plus 1 by Ho Ai by Ao. Since geometry of the heat exchanger is fixed, therefore the thickness of the inner area of inner pipe Ai, and log mean area of the inner pipe will be constant, and also K is not very much, therefore overall this resistance can be assumed to be constant, this conductive resistance. And here for simplicity we can assume that Ai is almost equal to Ao if thickness is very small. Otherwise you can consider there is no problem. Since cold fluid flow rate is kept constant throughout the experiment and the temperature does not change very much across the film, therefore this can be assumed to be constant, this one. So overall second and third terms will remain constant. We can take one constant for these two, C. Not working. C, and we can write 1 by Ui is equal to 1 by Hi plus C, where C is sum of the two resistances, conductive resistance plus convective resistance, which exist in the outer film. Next we will use the Dittus-Boelter equation. Nu means Hi by K. K is Kf, conductivity of the fluid. This equation is used when flow is fully turbulent. Nusselt number is equal to 0.023 into Reynolds number power 0.8 into Prandtl number power m. For the cooling, n is equal to 0.3, and for the heating, n is equal to 0.4. Here hot fluid is being cooled, so this is the case of cooling, and we can write PR means Cp mu by K F power 0.3. So this equation is applicable when Re is greater than 10 to the power 4. Prandtl number should be varying between 0.6 to around 150 or 160. Some places you can find around 100 or 120. I am taking 160. And L by D ratio should be greater than 10. Length of the pipe, diameter of the pipe. We are talking about the inner pipe, so DI. Length of the pipe divided by diameter of the pipe should be greater than 10. If all three conditions are fulfilling, then we can use Dittus-Boelter equation. Otherwise, we have some other correlations. Here PR can be easily found because all parameters are known. And in our case, we found the PR in this range, inside this range, and also L by Di ratio is greater than 10. And this one we already have considered. Therefore, we can apply this Dittus-Boelter equation. So now I can write HI is equal to 0.023 Di rho by mu 0.8 Cp mu by Kf 0.3 Kf by Di u power 0.8. Here Di and Kf both are taken in the right side. All the parameters except the velocity have been taken inside square brackets. All are constant except this velocity. Only velocity is changing of the hot fluid. And this is the velocity inside this pipe, not here. So you can calculate as I explained earlier. Since all parameters are constant, we can consider one single constant, say C1. So we can write HI is equal to C1 into u to the power 0.8. This can be put here. So we will have 1 by ui. This is the overall heat transfer coefficient HI from here. 1 by C1 into 1 by u 0.8 plus C. For different flow rates, we will have different overall heat transfer coefficient. We can draw a graph 1 by u 0.8 and 1 by ui. It will give a straight line. So intercept is C, slope is 1 by C1. Once we find C, we can find HO. So from here we can find HO. C means this one plus 1 by HO. So from here we can find HO 1 by C minus XW Ai by K AN. What is AN? Log mean area pi di d dLm into L. Length of the pipe and log mean diameter. Or we can say 2 pi RLm into L, where log mean radius. Outer radius of inner pipe, that is the sum of inner radius plus thickness, that is XW, minus inner radius of inner pipe divided by ln Ri plus outer radius divided by inner radius of inner pipe. Next we can find the inside film heat transfer coefficient Hi. So we can write from here 1 by Hi is equal to 1 by ui minus C. C known from the graph. We can write Hi is equal to 1 by ui minus C. So from here we can find the Hi. This is the Hi which is obtained from the experiment, and we can verify the inside film heat transfer coefficient from the experiment to the empirical equation. Similarly, we can compare the Nusselt number. For example, if we have to find the Nusselt number from the experiment, suppose this is the Nusselt number from the experiment Ex. Nusselt number from the experiment can be written Hi di by K. Kf. Hi should be given from here from the experimental value. And now coming to the theoretical Nusselt number, Nu, Th. Sometime back we wrote a Dittus-Boelter equation, again write 0.023 di u rho by mu Reynolds number of 0.8 power into Prandtl number Cp mu by k kf 0.3. So here we can find the Nusselt number from the equation, from the empirical equation where all parameters are known. This u is nothing but the velocity of the hot fluid inside the pipe, inner pipe, and other parameters are known. Therefore, we can find the Nusselt number theoretically, and this we can compare from the experimental value. From here, we can also find the heat transfer coefficient, inside field heat transfer coefficient theoretically. So this one is equal to, we can write Hi Di by K. Yeah. And from here we can find Hi. Hi is equal to Nusselt number, theoretical Nusselt number into Kf by Di. So both we can compare Nusselt number from the experiment, Nusselt number from the empirical equation, heat transfer coefficient from the experiment, heat transfer coefficient from the empirical equation. So these were few objectives which we saw in this lecture. Now I will stop myself and we'll meet in some other lecture. Till then, bye bye and thanks for the attention.